Hello, this is Mostafa Reisi. I'm an assistant professor of industrial and system engineering at the University of Florida. This talk discusses tensor analytics for systems of federated systems. As we all know, modern systems generate complex data. For example, in precision agriculture, a farm may be equipped with sensors, including hyperspectral cameras that are collecting data. Here is an example of hyperspectral curves that are collected at a farm. In condition monitoring, a process may be equipped with a large number of sensors that are evaluating the performance of the system. For example, here is a vehicle engine that is equipped with different sensors, and these are examples of these sensor measurements. In prognostic, a sensor can be used to evaluate or predict the remaining lifetime of equipment. For example, a thermal camera is used here to predict the remaining lifetime of an aircraft engine. Specifically, in many situations, the acquired data is high dimensional, meaning that there is a large number of features, or each data point related to a sample is high dimensional. For example, it's an image or is a curve in this case. The data can be also of high variety, meaning that there are different sensors with different attributes that are collecting data. And the data can be spatiotemporal. Here in this example, there is a spatial correlation within an image, and from one image to another image, there is a temporal correlation. In the sensor example, within one sensor, there is a temporal correlation, and from one sensor to another sensor, there is a spatial correlation. So now the question is that how to develop predictive models based on such HDHV data. When we say a model or predictive models, we mainly refer to a regression or classification models. For example, in precision agriculture, you may want to use these hyperspectral curves in order to identify whether a crop is healthy or unhealthy, or to predict the yield of the crop. Or in vehicle engine, based on the sensor data, you might want to identify whether the engine is faulty or not. While data is HDHV, the sample size is often small due to the cost of the data labeling. For example, in farms, one may need lab result and lab experiments in order to identify the crop has a disease or not. Or in engine example, an expert or technician needs to identify or evaluate the engine. There are different techniques that one can use to create these models. For example, generalized linear and nonlinear regression models can be used. However, these techniques cannot capture the correlation structure. Also, it creates a very large number of parameters that may not be tractable to estimate. Techniques such as principal component analysis, independent component analysis, and partial least square regression methods are also available, but they cannot exploit the ordering or spatial structure of the data. Functional regression approaches are also available, which are using the functional basis in order to reduce the dimensionality of the data. But these are mostly for profile data and are difficult to extend to higher dimensional data. Also, they cannot provide a unified framework for analysis of HDHV data and cannot handle multi-channel data effectively. Neural networks has shown promising results. However, they require a large sample size for HDHV data, which is often not available. So to address these challenges of the existing method, tensor modeling has been devised. So what is a tensor? A tensor is a multidimensional array. For example, a vector is a 1D tensor, a matrix is a 2D tensor, and then a cube is a 3D tensor. Data can be represented as tensors. For example, a video can be represented as a 3D tensor, and the multi-channel signals can be also represented as a 3D tensors. There are different modeling frameworks for tensors. Particularly here, I'm discussing supervised tensor modeling. For example, there are scalar and tensor models, tensor and scalar models, and tensor and tensor models. In scalar and tensor models, the input is a tensor of a large dimension, and then the output is a scalar that can be a real value or it can be a binary value, for example. The goal is to estimate the output given the input tensor using this model. In this model, a transformation of the expected value of y given the input is a linear model. And the goal is to estimate the parameters of this model. Different techniques can be used to estimate these parameters, for example, by maximizing the likelihood function, or location scale model, or in our case, LQ likelihood for robustness that is proposed by our group. Tensor and scalar models are also available, where the input is a vector and the output is a tensor, and the goal is to predict the output tensor using the input vector by estimating this set of parameters beta from a training data. Tensor and tensor models are also available, where the input is either one tensor or a set of tensors, and the output is another tensor, and the goal is to predict the output given the input. Here, the y is a sum of the contractions between the set of parameters b and input tensors. And so there are different techniques to estimate this b. Our group proposed multiple tensor and tensor regression. The main challenge in these modelings with tensors is high dimensionality of the parameters. And the solution to this is often low-rank embedding of the parameters. For example, one can represent the parameters by a set of factor matrices. And now estimating the parameter tensor transforms into estimating the factor matrices. Now that we know how to create the tensor models, each system can create their own tensor models based on their data. However, there are often a system with similar characteristics and goals. And if the system create their model in their own silo, then they cannot use the information from other systems. And this reduces the generalizability of the models, and also does not allow for transferring the data, transferring the model from one system to another system. To address this challenge, a system may share their data with a server where a global model is created. So each system has its own tensor data, which is shared with a server, and the server constructs a global model, and that global model is then sent back to each system where it can be used for example, decision making. But this has challenges. For example, not every system may participate in such a framework due to the privacy challenges or concerns. This framework requires expensive communication and computation infrastructure. Particularly, one needs a strong server to create a model based on all the data. Also, it creates a significant vulnerability in data leakage and cyber attacks by hidden adversaries. Because the data is shared, cyber attacks can happen at these channels. To address this, inspired by federated learning, we introduced system of federated systems. So in here, systems may share their models with an orchestrator that construct an aggregated model. So each system keeps its data locally and construct the model locally, and then share the model with the orchestrator. Then the orchestrator aggregates all the models and create an aggregated model, which is broadcast to the systems. These systems then use that aggregated model to update and personalize their models. So this approach maintains the autonomy of each system, preserve their privacy because the data is not shared, avoids the high cost of data transfer and communication, and does not require a centralized, expensive computation infrastructure. It also mitigates data leakage concerns because no data is shared. And also, because of the collaboration that exists in this framework, it facilitates HDHV data modeling. But these benefits comes with challenges. The first challenge is statistical heterogeneity, meaning that the data collected at different sites may not follow the same distribution, and therefore the models they create has disparities, which makes the aggregation a non-trivial task. Also, how to personalize these models at each local site based on the aggregated model is a question. Also, because the data is HDHV, there are common and distinct features that need to be identified at the orchestrated level and at the local level. How to do that is a challenge. Although privacy has been the main motivation of the federated systems, still one can look at the data, look at the models, and reverse engineering it to obtain information about each system. Therefore, still privacy is a challenge. Finally, systems with missing sensing modalities may exist. So not all systems may have access to all modalities, and therefore one need to take into account these missing modalities. In this talk, I'm mainly addressing the first three challenges. So we propose federated tensor modeling for system of federated systems. Here, mainly we're looking at scalar and tensor modeling framework. Here, there are T systems where each system has access to its tensor data and can build a scalar and tensor regression framework or model. Then each system will share its parameters to the orchestrator, where it solves an optimization problem to obtain the aggregated parameters. Then these aggregated parameters are sent back to the systems where they can personalize their model accordingly based on these values. Specifically, we're looking at models where yt given xt follows an exponential family distribution with canonical parameter theta, where this theta it is linear. It follows a linear model. So each local system will need to estimate its own parameters by solving this optimization problem. In this optimization problem, the first term tries to minimize the negative log likelihood value, and under the constraint that this set of parameters is decomposed into the factor matrices. Then, in order to personalize the model, we add this sparsity-inducing, in particular group sparsity-inducing penalty. And then to make sure that there is not much deviation from the central or the global model or the aggregated model, there is this proximity to a penalty term. So each local model solves this problem locally, and then at the global, the server or the orchestrator solves the aggregated objective function, where it tries to estimate the global value parameters. Notice that the first term does not have any global parameter in it, and therefore the orchestrator does not need to access to the data. Let me show some simulation results. So this is a simulation result based on homogeneous systems, and it's a regression problem. So here we're comparing our approach with different benchmarks. So in the first approach, each system creates its own model, and then the orchestrator aggregate them, and we eventually obtain the aggregated model, which is then used in a testing site. In the benchmark, in this framework, personalized version, the aggregated model sent back to each system, and then it's personalized, and then the personalized model are used in the test site. In another benchmark, each site creates its own model, and then and the model is used in the test site. And finally, in this benchmark, all the sites will share their data, and then accordingly, they build the model based on this shared data, and then which is tested on this testing site. Here is the result at in different scenarios, and as you can see, our approach performs superior to most of the benchmarks. And in particular, you can compare our approach to the shared data model. And because this is a homogeneous case, the shared data model is supposed to perform pretty well. However, here, our approach performs as good or even sometimes superior to the shared data model. Here is another simulation example that has heterogeneous systems, and this is a classification framework. We have different cases where the first case is very close to the homogeneous case, and case 4 is highly heterogeneous case. And we compare our approach to Fed averaging and the local modeling. And as you can see, the personalized model in the case 2, 3, and 4, which are heterogeneous, are performing superior to the rest of the benchmarks. As a case study, we consider predicting the class of an engine based on the sensor data. Here are some examples of the sensor data that are available. And this is an example of one particular sensor readings, lambda value upstream. And there are two types of it, type 1 and type 2. So we have 3 training sites or systems. Each system has 20 samples. And then there is one test site that has 19 samples. So we train models here, and then we test in this testing site. As you can see, the accuracy of our classification based on the aggregated model outperforms the rest. Here, this example, we're more closer to the homogeneous scenario, and therefore the aggregated model outperforms the personalized model. Here are some other notes. So to avoid, to further alleviate the privacy challenges, we may consider differential privacy to this model. Also, we may consider resiliency to compromised system. If some systems are compromised and they have data integrity issues, then how can we resilient when building the aggregated model? Missing modalities, as I mentioned before, is another challenge that should be addressed. And then sometimes some systems are more closer to each other or more similar to each other, and therefore ensemble nested federated modeling system will be considered. Thank you for listening to this talk. For further question or getting access to the codes, please contact or reach out to me at Reisi@ufl.edu. Thank you very much. Goodbye.